Great, thanks, Lydia. And so, somewhat coincidentally, actually, the recruitment pitch is somewhat relevant to what we're going to be talking about today, because we're going to talk about causality and randomized controlled trials, of which basically Lydia is like trying to recruit people in to participate in. So, actually, first I'm going to talk a little bit more about regression coefficients. That's just like a slide or two. Then we're going to start talking about causality. We'll talk about randomized controlled trials, which we often refer to as RCTs. So RCTs are the preferred method, the preferred tool for estimating causal effects of one variable on another, but as we'll discuss, they're often not feasible for the types of questions we want to answer in environmental economics. And then we'll probably talk about, maybe start talking about like multiple regression, which is a more general case of linear regression. So we were talking previously about estimating the relationship between two variables, basically seeing how well we can predict y using single variable x. But if we had multiple variables that we thought were going to be helpful in predicting y, then we could in theory build a model in which we were changing our expectation of y based on the values of, say, 3 or 4 x variables, not just a single x variable. So that's what multiple regression is, and we'll probably start talking about that. I think we'll also do a little bit of like group work somewhere between maybe period 2 and 3. Okay, so before we start talking about causality, so I talked about how you could always apply a descriptive interpretation to a regression coefficient, and I'll give another example of that a little bit later on in the lecture today. But before we start talking about causality, I just want to discuss a special case of linear regression that occurs pretty frequently in some of the studies that you'll see and sort of in the examples that we go through in class. So a special case of regression occurs when the right-hand side variable in regression, x, is binary. So when this is the case, we often refer to this binary variable as either being a dummy variable or an indicator variable. And it turns out this case is actually very common. So just to give a few examples, a first example would be a clinical trial, which is a randomized control trial. Again, something we're going to talk about in a little bit. But in a clinical trial, basically, if you have any sort of familiarity at all with how drugs are approved, that they have to show that the drugs are safe and effective. And in order to do that, what they do is they take a pool of patients that they want to treat, and they'll randomly assign them to two groups. One of the groups will be called the treatment group, and the other one is called the control group. The treatment group will get the treatment, and the control group doesn't get it, or get some like placebo pill or something like that. So in order to then estimate the effect that the treatment or the effect of being in the treatment group has on some outcome. So, for example, if you were developing a drug that was supposed to lower people's blood pressure, then presumably the main outcome would be the person's blood pressure after they've gone through this trial. So if you want to estimate the effect that being in the treatment group has on the outcome, you can actually just run a regression of y, which is blood pressure in this case, on x, which is going to be an indicator variable for whether you're in the treatment group or in the control group. So it's going to be a variable that we set equal to 1 if you're in the treatment group and 0 if you're in the control group. So that's a very common case in which you would be running a regression where your right-hand side variable is binary, or as we say, like an indicator dummy variable. Another case in, say, that's closer to like a type of problem that we often study in economics would be trying to think about, say, the effect of, or the relationship, really not the effect, the relationship between gender and some outcome y. So, y might be wages if you're interested in trying to sort of measure whether there's discrimination in the workforce or whether females seem to be at a disadvantage in the workforce. The first place to start would be to figure out, well, is there even a wage gap, in the actual data that we might be able to collect. So, in that case, what you would do is you would essentially run a regression of wages as the outcome y on a gender indicator, which would be, let's say, equal to 1 if the individual is female and 0 if the individual is male. Another case that we would be interested in sort of labor economics context would be trying to estimate the effect of higher education on wages. So that's something that perhaps should be of interest to you, since you are in fact going through a higher education program right now. And so in that case, again, the outcome there would be wages later on after you've graduated from college, and the right-hand side variable, which we would referring to as x, would just be a binary indicator, which is equal to 1 if you've gone to college and 0 if you're not a college graduate. So just for your own edification, it turns out that effect is very strong. So descriptively, it's true that college grads make much more than non-college grads. I don't think that's a surprise to anybody. But of course, some of that is probably due to selection bias, that people who go to college are, on average, probably have higher ability, even absent additional education, than those who don't. And so you don't know what the effect would have been, or what their wages would have been had they not gone to college. They still might be higher than the people who don't go to college. That being said, there have been studies where they've essentially been able to isolate random variation in whether or not somebody has gone to college. So you could think of it as essentially a case in, well, not so much whether or not they've gone to college, although that I think they've had some success in as well, but even just the effect of attending like a flagship state university versus like a lower ranked school. So people have actually been able to essentially it's not literally like they're performing their own randomized control trial, but effectively it works out that they have been able to use data where people are pretty much randomly assigned to whether they're going to attend a flagship state university or a lower ranked university. And even in that scenario, which is it's going to be a smaller effect than comparing going to, say, the flagship state university versus going to no university, even in that scenario, there's still a very high return to attending the higher ranked university. So probably good news for you. So when x is a binary variable, when it's a dummy variable, its regression coefficient has a special interpretation. So let's assume that x now is binary, or is a dummy variable, and we run a regression of y and x. It turns out in that case, the regression coefficient on x is equal to just the difference in means for the outcome between the group that has x equal 1 versus the group that has x equals 0. So what that means is that, for example, in the clinical trial, if you were to run that estimated regression of yi is equal to beta naught plus beta 1 xi plus epsilon I, so this is y is some outcome, probably blood pressure, xi is equals 1 if you're in the treated group, and it's equal to 0 if you're in the control group. So if you run that regression and take a coefficient on x, it turns out that coefficient is then just going to be the difference in mean outcomes between the treated group and the control group. So that's like, if you're not familiar with linear regression, I think that should be somewhat reassuring in the sense that presumably, if you didn't have a lot of familiarity with regression or with clinical trials or anything like that, and I just came to you and said, look, we randomly assign some people to the treated group and other people to the control group, and we want to estimate the effect of being in the treatment group on this outcome y, your intuition or first guess might be like, well, maybe I should take the average value of y in the treated group and compare it to the average value in the control group, and then the difference in those two averages would be my estimate of the effect of the treatment. And that would be, in fact, exactly right in that case. In the gender example, then, you would be comparing, when you run this regression, and x is now equal to 1 if you're female and 0 if you're male, you're going to be comparing the difference in mean outcomes between females and males when you look at that coefficient beta 1. And in the college example, you would be measuring the difference in mean wages for college graduates versus mean wages for non-college graduates. So in all of these cases, then, we're calling beta the difference in means. Okay, so this is going to be important later on in the course because it turns out that a lot of the sort of policy effects that we're trying to estimate are for policies that essentially are binary, like either the policy is in effect or the policy is not in effect. So in that case, then, the right-hand side variable in the regression is a dummy variable, and the coefficient on that dummy variable can be interpreted as the difference in mean outcomes between the two groups, or between when the policy is in effect versus when it's not. Okay, so estimating causal effects turns out to be tricky. Just as an example that I took from the Taiwanese government tourist etiquette page a few years ago, it says, quote, likewise, this is like advice for tourists, and they say, likewise, it's best not to give a handkerchief as a present, being something that is used to wipe away tears will actually bring them some kind of bad fortune that is a cause for crying. So this just demonstrates that the tendency to confuse or conflate correlation with causation is one that spans many cultures and eras. I think, based on any sort of reasonable science, we can safely assume that giving somebody a handkerchief is not by itself going to cause serious misfortune. But nevertheless, it is true that if you were to sort of collect data on handkerchief usage, it might well be the case that it would be correlated with unfortunate events because people would be upset and then they need to wipe away their tears. So correlation, of course, does not imply causation, but we need to actually define what we mean by a causal effect before we can sort of proceed and talk about how we would try to estimate some causal effect. So when we talk about the causal effect of x on y, what we're referring to is really the change in y that we would expect to observe if we, I'm going to call it experimentally manipulated x. So you could think of it as sort of, in a lab, you could think of it as we're coming in and as researchers, we're going to take x and basically change it exogenously by 1 unit and then see how that affects some variable y. And then sort of getting outside the lab and thinking more in terms of like social policy and so forth, what you want to think of is like a case where you're a policymaker and you're thinking about enacting a policy, and so you're going to come in and sort of from the outside, again, we call it like exogenously, come in and change a policy so that the policy wasn't in effect before and now it is in effect, and you'd like to figure out you'd like to know what the impact of making that exogenous manipulation is. So one way to think about this is that you want to think about what the effect of increasing x by 1 unit is going to be on y without changing anything else that affects y. So if you could sort of hold everything else that affects y constant and just change x by 1 unit, you would like to know what the effect on average of making that change would be. So economists will sometimes refer to this as the ceteris paribus change in x, so that's Latin for all other things being held constant. To go back to the example that we originally started with when we were plotting the data, we were talking about the potential impacts of daily air pollution on daily hospitalizations. And so what we'd like to estimate in those cases, or in that case, is essentially the causal effect of air pollution, and that's going to be the causal effect of air pollution on hospitalizations, and that's going to be the effect that air pollution has on hospitalizations if air pollution increases by 1 unit while nothing else that affects hospitalizations changes. So that's really going to be the issue, is that in a lot of cases when we're using real-world data that we weren't able to sort of generate in lab using like a randomized control trial, so in a lot of cases, when we see variation in air pollution, when we see changes in air pollution, we can't be certain that there aren't other variables that are changing as well that might affect hospitalizations or whatever the outcome that we're interested in is. So in general, a regression of y on x is not going to estimate the causal effect of x on y. So we know how to estimate, we know how to use regression to basically summarize the relationship between x and y, but just because we summarize that relationship doesn't mean that the relationship has causal interpretation. So again, the regression can be used to make descriptive statements, so we might use regression to say, look, it is the case in our data that when air pollution is high, hospitalizations tend to be high, but that doesn't imply necessarily, at least, that the regression estimates, or the regression estimates that you get are going to represent an effect of a ceteris paribus change in air pollution. And in fact, it's possible, and I would say likely, that when air pollution is high, there are other variables or there are other factors affecting hospitalizations that tend to be high. So for example, this is true that basically air pollution tends to be higher on hot days, and it's also true that on hot days people could suffer from, for example, heat stroke. So just because we see hospitalizations rise when it's polluted, we don't know if that's necessarily because of pollution itself or maybe just because of the heat or maybe some combination of the two. So then we say the regression coefficient is confounded or biased by other factors that are changing as x, in this case, pollution changes. So in order for that regression to actually estimate a causal effect, what we need is that x needs to be what we refer to as good as randomly assigned. So in social sciences, as in medicine, the gold standard of evidence is the RCT, the randomized controlled trial theory. And the reason for that is that if you think about, okay, so we define the causal effect of x on y as being the effect or the change in y that we would observe when changing x without changing any other factors that affect y, right? So in order to estimate that effect, then we need changes in x that are going to be uncorrelated with changes in any other variables that affect y. And the best way to achieve that is to randomly assign different levels of x to different people, right? So by definition, if I'm randomly assigning x, that means that x is uncorrelated with any other factor or any other variable because I'm just choosing it based on some random number generator. So in particular, we know that if x is randomly assigned, it's going to be guaranteed to be uncorrelated with other factors that could affect y. And so when x changes, we know that on average, other factors are going to be are not going to be correlated with that change in x. So that's not to say, remember, everything here is on average. So that's not to say that if you have a random assignment, that everything is going to be perfectly balanced or totally uncorrelated with x. So for example, if we were running like a clinical trial inside this classroom or something, we go through and basically take everybody in the classroom, randomly assign half the people to the control group, half the people to the treatment group, apply the treatment to the treatment group, and then see what happens, right? So we know that on average, all of the factors, like for any factor we think, we know that on average it's going to be about the same in the control group as it is in the treatment group because of the random assignment. But that doesn't mean that it has to be exactly the same. So like one factor would be, say, gender, right? So we might think like, depending on what the outcome is, like say that we're trying to all get taller, and so we have some like steroidal growth stimulant or something that we're applying. So it's like, obviously not likely to be legal. But in that case, certainly gender is going to be predictive of height. So we would want gender to be balanced between the treatment group and the control group. Otherwise, we might mistakenly believe that, or might mistakenly conclude that our treatment has an effect just because one group happens to have, say, more males than the other group. On average, because we did the random assignment, we will have the same proportion of females in both the treatment group and the control group, but it doesn't have to be exactly the same, right? Like you might end up with, I don't know what the actual proportion here is, but you might end up with like 62% females in the treatment group and like 59% males in the control group. So it wouldn't be perfectly balanced, but basically it's going to be close enough. And furthermore, we haven't gotten there yet, but we'll talk about doing statistical inference to take into account sampling variation, which is effectively what I'm describing here. That if we had arbitrarily large groups, a huge sample, then it would end up that after we ran our random assignment, there would be exactly the same number of females in the treated group as there are in the control group. It's actually exactly the same proportion of females as there in both the treated and control groups. But in a finite sample, there will always be some slight variation, but we can quantify that variation using statistical theory and then draw conclusions about whether the effects that we observe are due to a causal effect or might just be due to chance. So the clinical trial of a drug, I think, is really the best example of an RCT. So in that example, as I said, X is going to indicate whether a patient is in the treatment group versus the control group. And since X is a dummy variable, we know that when we regress Y on X, that's going to measure the difference in means between the treated and control groups. So, for example, if we were studying whether a drug reduces blood pressure, the regression coefficient measures the difference in average blood pressure between the treatment and the control groups. And since X is randomly assigned, we know that on average all other factors should be identical, in expectation or on average, across treatment and control groups. So, in particular, I think this is like a case where contrasting the randomized control trial versus what you would do, or the estimate you would get if you were to simply go into the population and survey people about what their blood pressure was and whether or not they were using a blood pressure medication. That contrast is particularly stark here, right? So let's consider the example, the second example I gave, where you don't run the randomized control trial. Right? So instead, you're like, well, I want to know, how effective this blood pressure medication is at lowering people's blood pressure. So what I'm going to do is go draw some big sample from the population of the United States, ask them, are you on a blood pressure medication, yes or no, and then measure their blood pressure. So come in and put on the blood pressure cuff and figure out what their blood pressure is, right? And then I'm going to run a regression of blood pressure, which is Y here, on whether or not you're on blood pressure medication, which is X, and interpret that coefficient that I get as potentially being the effect of the blood pressure medication on your blood pressure. So if you think about what's going to happen there, the only people who are actually on blood pressure medications are those who have high blood pressure to begin with, right? So we know that on average, if you're on a blood pressure medication regime, we know that on average you're probably somebody who already had high blood pressure. And so even if the drug itself is effective, it's probably not so effective that it's going to completely cancel out the fact that you already had hypertension, which is what we call high blood pressure. And so you're going to estimate that you're probably going to get like a positive value of beta 1. So even though the drug itself may have a negative effect on blood pressure, or may lower blood pressure, reduce it, you're going to conclude that in fact it increases blood pressure because the people who are taking the drug were self-selected specifically because they had high blood pressure to begin with, right? If you already had low blood pressure, there's no reason to be on this drug. So you're going to get like a positive beta 1 there, even though the causal effect of the drug, assume the drug is effective, the causal effect of it is actually to lower your blood pressure, which would imply a negative beta 1. In contrast with the RCT, what we're going to do is randomly assign. So we're going to take a group of people, probably people who had high blood pressure to begin with, because it's not clear why we want to treat people who don't have blood pressure problems. But we'll take some group of people, and then we'll randomly assign whether or not you get the drug. And so because of the random assignment, we know that the people who were treated will not on average have had higher baseline blood pressure than the people who were not treated. And if the drug is effective, we should see that the treatment group ends up with lower blood pressures by the end of the experiment than the control group. So that's really the draw of RCTs. In social science, they're not as common as in medicine, and the reason for that is basically that it's usually infeasible to conduct them. So first of all, they tend to be expensive, and so like a drug company can afford to potentially pay millions to run these randomized controlled trials with patients and everything, because they know that if they're successful and show that the drug is effective, then they can recoup those costs when they start selling it. But like social scientists who are just operating off of like relatively small scale grants and stuff, are not going to be able to fund large scale RCTs. So you have the issue of expense. You also have the fact that in many cases they would be considered unethical. So if we're thinking about trying to randomly assign daily pollution levels, that would actually be feasible if you think about it, but it would not be ethical. So the way it would be feasible is lowering pollution is expensive, but like raising it isn't necessarily expensive. So you could probably produce like a highly polluting device that the only goal of it was to emit pollution for not that much money, and then you could sort of randomly turn it on one week and not turn it on another week, and keep doing that over like a long period, and essentially you would be generating random variation in whether it was a lower pollution day or a higher pollution day. That would be possible. Then you could test the effects of pollution on a variety of outcomes, but I think it's safe to say that the EPA or the California equivalent of it would not allow that to occur as soon as state government. It's also the case that the campus Committee for the Protection of Human Subjects would also not allow that to occur. So in many cases, RCTs are basically either logistically infeasible, too expensive, or considered to be unethical. So instead of actually having an RCT, we hope, or instead of actually doing our own RCT, we hope that instead XI is as good as randomly assigned. So that being said, I just want to also say, there are, in the past decade or so, like social sciences have really, well, at least economics, like I guess psychology was always probably doing experiments, but in economics, they've really started to adopt randomized control trials in specific settings much more than they used to. So, for example, what Lydia was just saying today, so that's the type of research she does is more in sort of like the behavioral economics and psychology field. But in that case, they're literally doing like lab experiments where they have you come into lab and then sort of randomly present different people with different scenarios and see how they react to them. And they put in like real stakes. That's why you get paid. And your payment, she says, like, well, you're guaranteed at least $10 an hour, so that's sort of the base payment. And if you do well in the game, then you'll get more than that. In some cases, substantially more than that. And that's to give you essentially an incentive to actually perform well and sort of be behaving in a way that we would think is consistent with a real world scenario where you face monetary incentives. So that's one example where they've been doing sort of lab experiments, randomized control trials for quite a while. In development economics, they've been doing field experiments for the last 10 years. So they'll like go into Kenya or like someplace in India or something like that and start randomly assigning things that they think might be helpful to populations there. So for example, one of the first large scale RCTs in development was something called Progresa in Mexico, where it was sort of this combination of they would go in and randomly give both cash. It was called a conditional cash transfer. So they would go they go into a village and choose randomly choose some subset of the households there and give them cash if they met some conditionalities. So basically, it's like if you send your kid to school and you make sure they're